but then again, it's a lot of your participation too. It looks like you've been really going after this aggressively. Congratulations.
Thank you.
All right, we're at 7:30. I guess Bruce or Dave, when do we want to start rolling?
Well, first of all, welcome to everybody to our rather different edition of the Chester County Astronomical Society, since we're on a different night and we are completely Zoom, the first time in a few months here. But I would just like to bring up a couple of things. First of all, many thanks to our speaker, Steve Levine, for agreeing to accommodate us in this sort of off day from our regular thing. Oh, he's drinking to a cheers to us as we speak. But also, this is great that everybody was able to get the word about the switch and come over to Thursdays instead of Tuesdays. So it's good to see you all here. I would also like to mention that next month, we do not have a regular meeting. We have a holiday party instead. And since our membership has now grown to, what are we up to, about 140 now, Don?
140 or so, yeah.
Wow.
It's getting a little busy to be able to have this in somebody's home anymore, especially if everybody wants to show up. So this year, we decided to have this at the event, our holiday party in Avondale, Pennsylvania, at a brew pub called Be Here, Behere. It's on 122 Pennsylvania Avenue in Avondale, and it will be December 14th. So we already have a good response. We have enough people to make it a go. The restaurant normally isn't open on Tuesdays, but they're opening it especially for us. So get the word out to the other members, let them know that it's going to be a great party. They have their own handcrafted brews. They have some non-alcoholic brew as well as that they serve there. And great appetizers. Features a lot of the local mushrooms from that area. So it's just an incredible place. So put it on your calendar, December 14th. That's when the holiday party will be, and I hope to see you all there. And
The beer is awesome.
Say again?
The beer is awesome.
Yeah, the food is awesome, yeah.
It's really good. Especially the mushroom cheesesteak was outstanding. And I don't even like it. So anyway, I'm going to turn the meeting over to Don, and he's going to fill us in on a couple of things.
All right, well, I'm going to go right to sharing the screen here. I'm going to start briefly with Stellarium, but I do have one other thing I want to show then. So this was from Friday night. We're out at Brandywine Red Clay, and this is the looking south. I want to show you what we're really happy to experience with Chris Trunk's telescope. So this is around 8 o'clock, and if you watch what happens here to Jupiter, as we watched, it didn't take long. I'm going to make the time go a little faster, but Ganymede came around from the back, and we actually could see the shadow on the planet. It was really cool.
Oh, wow.
Really cool. Really enjoyed it. Now, we didn't stay long enough, but then also Io came out, or Io, whatever it is, came out from behind the planet also. Either in front or behind. I'm not sure which it was. But it was great. We had a nice time seeing that. The other thing, I'm going to go a little bit later at night now, because someone want to show you. We did see Uranus, but I want to take a moment and highlight something else over here. Here's Cetus, the whale or the sea monster, and I want to highlight this star Tau Ceti. And to do that, I'm going to switch to another screen, and I want to show you a few things about Tau Ceti. Can you see my slideshow? Okay, so Tau Ceti, we're just looking at it on Stellarium. It's a star in constellation Cetus, and it's similar to our sun, and it's just under 12 light years. It's fairly nearby, and it's a closest solitary G-class star. I was set up here last night, Barb and I, we saw Tau Ceti live in the eyepiece, and we could see it naked eye and then find it better in the eyepiece. But since it's so close and similar to our sun, it's often a target for extraterrestrial intelligence search in SETI. And it's been in science fiction, literature, TV shows, movies. And, there's evidence that, now this is our sun, and this is Tau Ceti in comparison. So it's pretty similar, like 80% of the size of our sun, but at least 4 planets, all confirmed being super Earths, okay, orbiting Tau Ceti. 2 of them in the habitable zone, which is one reason why we keep listening to hear ET call home from there. But it's been in 30 books, it's been movies and TV shows, Star Trek Wrath of Khan, several several Star Trek shows. In The Expanse, and many Expanse fans, this Tau Ceti was where the Nauvoo was going to be heading to until it got hijacked by the powers that be. I don't know what Tau Ceti was doing in Barbarella, but it was in Barbarella. And it's been in numerous comics and computer games. But one reason I want to really highlight it is because Jack McDevitt is on tonight with us. Jack is a member of our club. So he wrote a story called Tau Ceti Said What? And here you go. There's Jack's name. This is the November-December issue of Asimov's. And I can tell you, if you get a chance to pick it up, you can get it at, I got my copy up at the Barnes & Noble in Exton. You can also get digital online. But, Jack became a member back in like 2016. I think this is over in Europe at a signing where he was at. And the way we got to know Jack, I read one of his books, Cryptic, wonderful book, wonderful collection of short stories. And I wanted to use this picture from his book, and I'm very careful about copyright. So I actually wrote to Jack, say, can I use it? He said, yeah, sure, but tell me about your club. So we exchanged a few emails. Turns out he spent a lot of time in Philadelphia, English teacher, naval officer, taxi driver. And so he actually came and visited us. So I wrote this article about this book. He visited us in October 2016. Okay, and Jack is well known in the literature world. He's a Nebula Award winner, and been nominated numerous times for the Nebula. Won it once, and came to visit us back in October 2016. So if you want more information, you can go then to the October newsletter. This is the cover of it, and I wrote more about Jack and his visit that he came to us. So it's fun when you look at Tau Ceti, and Jack wrote a story about it. And I'm not going to ruin it for you, but I can tell you that there are some alien signals are included. All right, so that's all I'll say. And one last thing, Jack did tell me we ought to look for the Asimov edition in the spring. I think it's the March, April edition, Jack, is that right?
That sounds correct.
Yeah, there's going to be a mention of a astronomy club located in Westchester, Pennsylvania. So we all have to read that story when it comes out, all right?
Wow.
Enrollment is going to skyrocket, Don.
The title of that story is the Gold Signal.
Sorry, what's it called?
The Gold Signal.
The Gold Signal. All right, so there's a mention of an astronomy club in Westchester, Pennsylvania. So we all are going to have to sign into that one. So
Yeah, it turns out you guys are going to survive a long time.
So I'll just highlight a couple other things. We were out there Friday night. Here's Uranus. The center on that. And it was not too hard to find. We started up here at Hamal, star hop down to this double star, then down further. And again, we did it with the big binocs. We didn't really have a real clear view of it, but we could definitely see the planet. Didn't quite get the color. Certainly didn't get any moons, but it was fun to see. One of the really nice scenes that night, of course, was Saturn. Saturn's always amazing, but even more so, seeing this guy here. Double cluster is hard to beat. Hard to beat on a November night when it's a little chilly. In fact, my feet felt like blocks of ice, but the double cluster and to see them in large binoculars is truly stunning. Truly stunning. What else were we seeing, Chris? Do you remember?
Oh, boy.
Pete was out there, about 8 or 10 of us out there.
Alberio up for a while. That was pretty nice to look at.
Which one?
Yeah. Alberio.
Abirio, yep.
Yeah.
Some of
Those
us were
colors, you
looking
can
at
tell.
custom.
That was nice about that. You could definitely see the difference in the color.
Yeah, I know we looked at ET. I know we looked at ET. There's ET, or the dragonfly. But it was cold, but it was clear, very steady, not terribly transparent. We did look at Andromeda, of course. I mean, how can you be out November evening and not look at a galaxy when you have the chance?
Right.
Look at Andromeda. So it was fun. So I think that's enough for me for now. I'm glad Dave mentioned the holiday party. We're all set for that, and hopefully we'll get a lot of people come out. All right, Bruce, back over to you. Jack, thanks for attending tonight. I appreciate it.
Oh, my pleasure. Thanks for letting me in.
So hello, everyone. Real privilege to introduce Dr. Steve Levine. Steve is a radio astronomer from JPL, and he is the project scientist for the Juno mission and a lead co-investigator for the Juno microwave radiometer. And as he mentioned before, he showed us a picture of a radio telescope. He is the lead scientist for that telescope, the Goldstone Apple Valley Radio Telescope project. So he has been at JPL for, wow, now over 30 years. And during that time, he has done radio astronomy in a variety of venues and locations, including, hard to believe, the South Pole, as well as studied the cosmic microwave background radiation, done some SETI work, and also measured magnetic fields in star-forming regions. So quite a diverse repertoire, but I think Steve's real focus is Juno, and that's what he's going to discuss tonight. Highlights of the 5-year mission, its discoveries, and a preview of the planned extended mission of Juno to Jupiter. So Steve, again, thank you tremendously for coming and speaking to us. Thank you.
My pleasure. And what I would say is you listed some of those topics that basically because all of my career decisions are made on the basis of, that sounds like fun. So tonight we're going to talk about Juno and Jupiter. Let me share my screen here. And put it in presentation mode so it's a little bigger. Okay, are you all seeing a
Yep.
title slide?
Looks good. Yep.
Great. So I titled this, It's a Whole New Jupiter, and you'll hear why in a few minutes. So let me start with just kind of an overview of what Juno is. So Juno is the first solar-powered mission to Jupiter, the first time anybody sent solar panels further than about the asteroid belt. I won't list everything on the slide here. I'll just point out we've been at Jupiter now for about 5 years, and it's a spinner. It's a polar orbiter, so it goes over the poles of Jupiter. It took us 5 years to get to Jupiter, and basically what we do is every 53 days, although we just changed the period, so now it's every 43 days, we fly by really close to Jupiter and try to learn about the giant planet. And I'll tell you a little bit about the extended mission in a bit. And I also want to mention a couple of things. One, this slide is getting crowded. I may have missed a few, but I think this is every magazine or scientific journal on which Juno got the cover, one way or the other. So we've had a lot of interesting science results, a lot of stuff come out, and I can't possibly tell you about all of it. So I've picked a few things, and I'm hoping to leave a whole lot of time for questions at the end. And I also wanted to point out that this is a principal investigator mission. And actually, I think that's important, if a little bureaucratic to think about. So the way NASA does projects is the really, really big ones are run by committee, and there's a science team and there's a project manager, and all of the major decisions have to go through a whole big process, and NASA picks the team and puts it all together. But the smaller ones are done as proposals by a principal investigator. So one person puts together the team and institutions who are going to do it and proposes to NASA, hey, why don't you give us money to do this? So Juno at the time, and I think still is, but certainly at the time it was selected, was the largest mission ever done as a principal investigator mission. And it's been a spectacular success. And I think in part because of that, because we didn't have to run it by committee. We had one person who was at the top and could make the final decisions, and he knew what he was doing. He could delegate to people, and we could pick a team that worked well together. And the team was put together as a team rather than having people compete to be on it and so forth. So I just thought I'd put in a little plug for doing things a little more efficiently that way. Okay, well, let's talk about the fun stuff. So what you ought to be asking when I tell you we sent a spacecraft to Jupiter is why, right? What are we trying to accomplish? So the key to understand why Juno was sent to Jupiter is to think about our solar system on a larger scale. So if you imagine you were, say, coming from Tau Ceti, you were an alien coming to the solar system, and you looked around and you found the sun, and you said, okay, I'm done. That's all there is. I found everything. You'd be well over 99% right. 99, more than, I think it's 99.8 or something percent of the mass in the solar system is the sun. But if you looked really carefully and said, okay, I found Jupiter, now I'm done, you'd be more than 2/3 right, because more than 2/3 of the remaining mass is in Jupiter. If I took all the other planets and all the asteroids and all the comets and everything else in the solar system except the sun, smushed it all together and made a giant planet, it would be less than half the mass of Jupiter. Furthermore, while we don't know everything there is to know about how solar systems form, one of the key things we are pretty sure about is Jupiter formed first. So that means if I want to know how did the solar system form, how did the Earth form, where do we come from? Basically, we come from the leftovers of Jupiter. So to understand all of that, we need to understand how Jupiter formed. And Jupiter is one of the first objects anybody ever looked at with a telescope. Galileo looked at it 500 years ago. We learned a bunch of things, but until Juno got to Jupiter, basically, there was a lot we didn't know about what's beneath the clouds. Almost everything we knew about Jupiter, we could see at the top of that giant atmosphere in the clouds. Basically can't see beneath them. And so the main purpose of Juno was to send something to Jupiter to peer beneath the clouds. Now, we can't really just dive in underneath the clouds because Jupiter is a giant planet, and its mass means that the pressure gets ridiculously high a tiny fraction of the way into the planet. You go a few hundred kilometers into Jupiter and you're getting to pressures and temperatures that are so high, it's really hard to build anything that can survive. So we didn't plan to send a probe into Jupiter, although I will say when NASA first put out the opportunity, hey, you can propose to these possible things to put a mission together, they actually titled this one Jupiter Polar Orbiter with Probes, plural. So they were thinking, drop more than one probe into Jupiter. And our response was to put in a proposal that said, no, we don't think we should put any probes in. And instead, we have this microwave radiometer. We think we can do the job better over much more of the planet and looking much deeper by looking through the clouds instead of trying to send an object down in between. And they selected us. And the way we're doing it is, in order to study the origin, how do you figure out how Jupiter formed? We need to know what it's made out of and what its structure is like on the inside. So we need to figure out whether there's a dense core where the heavier elements fell to the middle, how much water there is, because in the early solar system, water was by far the most abundant solid. Frozen water, ice, was what you make planets out of, basically. The interior, what's the structure like under there? How do things move? How is the magnetic field formed? And what does that tell you about the interior? The atmosphere, this giant planet, it's mostly gas. We wanted to understand the atmosphere. And then the magnetosphere, it's got this enormous magnetic field. That's what you're seeing here in the picture with the lines. is a representation of what Jupiter's magnetic field looks like. And we wanted to understand that, especially because when we looked at how to do this, we concluded, well, we obviously want to get really close to Jupiter, because if you want to study beneath the clouds and measure its magnetic field, which comes from deep inside, or use a microwave radiometer, which can see through the clouds, or measure the gravity, because that comes from deep inside, you need to get close to the planet. But Jupiter is surrounded by high energy electrons trapped in the magnetic field, radiation belts, like the Van Allen belts here on the Earth. And they can fry the electronics on the spacecraft. So everybody else who's ever sent a spacecraft to Jupiter sent it far away from the planet, tried to orbit the planet if they were going to orbit from way outside these radiation belts, and orbit in the plane of the equator so that you could look at the moons and all of that stuff. And what we said is, well, we'll basically give up on the moons so that we can get really close to Jupiter. And instead of trying to say outside the radiation, we're going to duck under it. So that's what that white line is, showing an example of the trajectory of the spacecraft. So you start really far from Jupiter at a big, long elliptical orbit, come in over the pole, up where the magnetic field is excluding the radiation belts. You don't have much damage to the spacecraft. Come screaming by at 30 kilometers a second, fly by the planet, get a little bit of damage, but not too bad in the radiation, do all the measurements, and then fly down out the other side at the South Pole and spend another 53 days before you do it all over again. That's our basic plan. I've listed a bunch of instruments on the right-hand side. I'm not going to take the time to go through all of them because I want to hurry up and get to questions, but feel free to ask me about any or all of those when I do get there. And I think that's probably enough to move on and tell you a little bit about what have we learned. So the first and most important thing we learned is humility. Before Juno got to Jupiter, we had a lot of ideas about what Jupiter was like and what the interior would look like. And we were measuring a whole bunch of things in a whole bunch of different ways, doing things that fundamentally had never been done before at Jupiter, measurements that had never been made. Essentially, every single one of those measurements gave us a surprise. Jupiter did not look like we expected it to. In fact, for our very first science pass, the first one of those flybys of Jupiter that we did, when we started looking at it, we had quite a bit of discussion within our team about what the heck is going on. And Mike Jansen, who's since retired, but was the lead at the time for the microwave radiometer instrument, which had just produced this puzzling, bizarre set of data, said, face it, it's a whole new Jupiter. You're going to have to live with it. And I love that. I use that in every talk because that's really what's going on. We have to learn that no matter what you think you know, until you've measured it, you don't know it. And when we got there and measured, we just got a ton of surprises. So as I say, I can't possibly list them all. I've picked out half a dozen of what I think are the really big, most important ones. And I'll talk about them plus a little bit more in an effort to give you some information and hopefully get you to ask me a bunch of questions at the end, because that's the fun part. Okay, but just to list through a few of these, the deep atmosphere is not well mixed. So that's a simple sentence, but let's think about what it means. We're looking at a giant ball of gas. Jupiter is mostly hydrogen and helium. And it's big enough and high enough pressure and everything so that the sheer mass of it and the gravity squeezes the interior so that that hydrogen and helium do funny things, and they're not gas, they're liquid down in the center. But nonetheless, I've got this giant ball of fluid and it's rotating every 10 hours, so pretty darn fast compared to, say, the Earth at every 24 hours and 300th of the mass. And everybody thought that once you get below where the clouds are, and you're deep below where the sun shines, you basically, in the dark, everything's a fluid, there's no solids, there's no phase changes, there's no obvious big chemistry going on, that pretty much one spot should look the same as any other. Maybe there's some vertical structure because the heavy stuff would sink to the bottom, but nobody expected that there'd be structure across latitude deep inside Jupiter. Well, when we got there with the microwave radiometer and we looked, we saw structure as deep as we can see. So we'll talk about that in a little bit. Next is we were the first spacecraft to fly over and get good pictures of the north and south pole of Jupiter. And it doesn't look anything like the sideways view. You've all, I hope, seen Jupiter in a telescope. We've got a little picture of it from the side here. If you looked at the first picture, and in fact, when we first saw the first picture we got of the North Pole of Jupiter from when Juno flew over, genuine reaction of a bunch of people was, is that the right planet? Did you guys actually, did you get the wrong picture up on the screen? That doesn't look like Jupiter at all. It just flat out doesn't look at all like it does from the side. So we'll talk about that a little bit. We went looking for a dense core. Basic idea, it's a fluid, the heavy stuff should sink to the middle, right? And we were very interested in the size of that core. The theories ranged from 3 to maybe 20 times the mass of the Earth, but everybody thought it would be a dense core way down in the middle. Wrong. What we see is about the right amount of material in the heavier stuff that we expected, at least within that broad range, but it's extended. It's something like half the radius of Jupiter is this fuzzy core, and it's dilute. It's not as dense. So another big mystery to try to figure out. The belts and zones, the orange and white stripes that you see in a small telescope, those are jet streams moving in opposite directions at the top of Jupiter's atmosphere. Nobody knew for sure how deep they were, but generally most people expected that they're shallow because water condenses out a few kilometers into the planet. I don't remember the exact number, but certainly less than, say, 100 kilometers at a pressure, which is where we usually think of it, the way we usually think of it, about 10 times the pressure here on the Earth. So people thought pretty much all the weather, all of the sort of interesting stuff in terms of things moving around and everything, most of that should go away by the time we get deep. And so those belts and zones are probably shallow. Well, they go 3,000 kilometers into the planet. So another surprise. Magnetic features. The magnetic field of Jupiter is primarily generated by an ocean of liquid metallic hydrogen deep inside the planet. So I love to stop and say and talk about that when I give talks like this. Think about what that means. It's liquid metallic hydrogen. Hydrogen gas, the lightest element there is here on the Earth, would float up into the sky. If you squeeze it under enormous pressure, like the conditions at Jupiter, the interior where it is tens of thousands of degrees Kelvin, very hot, but squeezed even more. The pressure, it gets up to pressures several million times the pressure here on the Earth. By the time you squeeze hydrogen to about 2 million times the pressure here on the Earth, not only have you made it a liquid, but you've squeezed the electrons right off the atoms. It conducts electricity, it's a metal. So it's the swirling motion of that liquid metallic hydrogen that generates the magnetic field. And we knew that, we were pretty sure of that before we got to Jupiter. And the expectation was, okay, that's maybe a third of the way down into the planet from the surface. So no matter how complicated a magnetic field I make with that swirling metallic hydrogen, as I look at it from far away, so I'm looking at it from above the surface, right? Even though we're flying really close to Jupiter to be able to measure the magnetic field, we're not inside the planet. So if it's generated a third of the way down, then the complicated parts of the magnetic field have room to fade away. If you study what happens with magnetic fields, the simplest term you can have is a dipole term, like a bar magnet or the Earth's magnetic field. If you add complications, you bend those field lines, wiggle them around and make more complicated terms. The further away from it you are, the further away from the source, the more those fade away. The dipole fades away too, but it doesn't fade away as quickly with distance. So how complicated it is tells you about how close you are to it, how well you can see it. We found a magnetic field that was much more complicated than expected. So it can't all be generated down in the middle. Something has to be happening to affect the magnetic field closer to the surface. We have a recent result, which I'll talk about related to that, where we actually see the magnetic field distorted by the motions of Jupiter's atmosphere. So that's pretty cool. And then finally, I'm going to talk a little bit about shallow lightning and what that tells us about the overall mystery of what's going on with Jupiter's atmosphere. All right, so let's dive into a few of these. And I'm going to start with the deep atmosphere is not well mixed. So when you look at Jupiter in the microwave, what you're doing is looking at the natural glow, what's called black body radiation from Jupiter. Essentially, it's the same thing as if you heat up a lump of something and get it red hot, it glows red. You get it hotter, it glows white, right? Well, if you get it not very hot at all, say room temperature, it glows mostly in the infrared. And if it's even colder than that, it'll still glow, but mostly in the microwave, in radio waves. But when you get hotter, you get more radio waves. It's just you get even more infrared. When you get hotter than that, you still get plenty of infrared. You get more infrared from heating it up. It's just you get more visible light now too. So if you look at Jupiter with radio waves, you can see right through the clouds. And what you're seeing is the hot interior. Remember, it's tens of thousands of degrees down in the middle. And that, by the way, is because it's still cooling off from the heat of formation 4.5 billion years ago. It's just so big that 4.5 billion years isn't long enough for it to cool off. Okay, so we look down into the planet, 6 different channels, 6 different wavelengths, looking at a bunch of different angles. Let us see into the planet a few hundred kilometers down to pressures of a few hundred times the pressure here on the Earth. And what we saw was the opacity, how well you can see into the atmosphere. So was dramatically different at different latitudes. So what I'm showing in this plot, I'm writing in the lines for a minute, just look at the colors, is for the first few passes where what we could see really easily, the thing that absorbs the microwaves the best, at least in terms of how much material there is in Jupiter, is ammonia. So this is a rough translation of what we saw into how much ammonia there was. And it's latitude on this axis, so from south to north, and it's pressure on this axis, from high pressure, that's deep inside, to low pressure, that's the top of the atmosphere. And then the color is how much ammonia corresponds to what we saw with the microwave. What we saw is right at the equator, but notice not exactly at the equator, a little bit north, it is kind of more or less uniform with depth. But you go just north of that, and there's a whole bunch of ammonia missing. And you go south of that, and or further north, and what you see is ammonia at the top starting to fade away and then come back again down below that at greater depth. So that was the first image actually that led us to say, what the heck is going on? And it's a whole new Jupiter. We still don't know exactly, but we have an idea now that seems to kind of work, and it's pretty bizarre. So the idea is mush balls. If you look here on the Earth at storms, one of the ways you can get a storm produces hail. You can get a hailstorm. And what that is droplets of water carried by an updraft way up high in the atmosphere to where they freeze. And then they fall down to where it's warm and water's a liquid again, pick up more water, but the updraft carries them up again and they freeze some more. So they go back and forth a few times, picking up water ice until finally they're too heavy to get carried up, and they fall down through the updraft and reach the ground. That's a hailstorm. That is here on the Earth, however. Jupiter is a lot more bizarre. And in addition to water, it has ammonia in its atmosphere. Well, you may know ammonia works as an antifreeze. So the theory that's Tristan Guillot and Scott Bolton put forward was that what's happening is drops of liquid water pick up a little bit of ammonia dissolved in the water. That keeps them from freezing as easily, so they can go higher and lower than you might guess. You have enormous storms on Jupiter carrying them up, and you get this sort of hailstorm in which big balls of frozen water with mushy Windex inside, ammonia and water is sort of Windex, get carried up and down and melt or vaporize way at the bottom when they finally drop out and stay frozen way up at the top. And what that does is let you carry some of the ammonia and the water up above the water cloud, so above this region, and then drop it down way below the water cloud, down into this region. And you don't see it with the microwave radiometer when it's frozen inside the water balls, the mush balls. So that kind of sort of explains the theory. And of course, a lot of people said, yeah, but that's crazy. That sounds way too complicated. However, it starts to kind of fit. It fits what we see for how much lightning there ought to be. It fits, here's a prediction of what the plot on the left ought to look like if you believe the mushball theory and look at the winds and where we see storms and stuff. Not too bad. And it also predicts that should mean there's places where the storms carry water way above the water cloud. So that's something you can look for, because lightning requires water as a liquid, a solid, and a gas all in the same place. The way you get lightning is solid water, ice, carries electric charge and separates it, and then it zaps itself back together, and that generates a lightning bolt. So in 2020, Heidi Becker, who's using the star camera from the spacecraft, so that's the camera that's supposed to be used for navigation. Well, she's figured out a way to use it for science as well, because it's really good at taking pictures in the dark. She took a couple of pictures with it of near the North Pole of Jupiter, Jupiter's northern hemisphere, in the dark. And in this particular image, got a couple of lightning flashes captured in the photograph that are at very high altitude, well above where the water cloud is. And the way we know that is the size. You're looking into this great big deep atmosphere. So if the lightning flashes were down where the water cloud is, then the light would scatter on the way up to the spacecraft, and it would make a bigger dot of light than you see in these lightning flashes. We're still working on it to try and get more and so forth, but that's a pretty good handle on the idea that, yeah, you can get lightning on Jupiter at shallower depths in the atmosphere, way up above where the water clouds are. And that lends a lot of credence to this crazy mushball theory, because now you have another reason to expect ice is being carried way up above the clouds. So that's kind of where we are with those pieces of it. Another point that I'll make about the deep atmosphere that kind of goes with that same deep atmosphere isn't well mixed thing is storms, or vortices, if you like better, cyclones. We have a paper just out in Science about a week ago in which we finally got all the numbers together and were able to show conclusively for at least 3 of these storms that they go well below the water cloud. So the one on the left is the Great Red Spot. If you look at the picture on top, that's what it looks like in visible light. Then you look at each of our 6 radio channels, and you can see that the storm is still visible all the way down in our deepest channel, 350 kilometers into the planet. The water cloud is way up here at less than 100 kilometers, maybe 50. So we are looking much deeper than the cloud of water, than where clouds are, much deeper than where sunlight goes, and we're still seeing enormous storms. That one's a storm bigger than the whole Earth. These others are smaller, but they're still, maybe the size of Texas or something. And some of these storms penetrate hundreds of kilometers down into the planet. So whatever's going on, it involves stirring up the atmosphere much deeper than you might expect from just analogy with the way weather works here on the Earth. Okay, well, that brings me to the North and South Pole. Now, we got lots of great visible light images of the North and South Poles, and that's in fact how we first found these cyclones. But it's a lot easier to see them in the infrared pictures because the infrared camera can see in the dark. So if you think about looking at the pole of Jupiter, whether you're looking at the North or the South Pole, half of what you're looking at is always going to be in the dark, right? So the sun's illuminating it from the side. So you can get much nicer images that show the whole thing in the infrared. And I've got a couple of these here. The one on the left is what the North Pole looks like. And we see this central cyclone. That's maybe a little bigger than the United States, surrounded by 8 smaller cyclones, still pretty darn big. And it's been steady like that for the entire 5 years of the mission. So whatever is making that pattern, the pattern is pretty stable. And in the south, it's similar, except it's 5 cyclones rather than 8 surrounding a central cyclone. And you can't tell from this picture, but these are slightly bigger. And if you watch that for the duration of the mission, and get picture after picture every 53 days, we actually saw a 6th cyclone kind of push its way in and get rejected. So not only is the North and South Pole of Jupiter a little bluer and less organized into belts and zones than the planet looks from the side, but it has these crystals of cyclones, these vortex crystals they're called, or at least similar to vortex crystals, where you have giant storms that are stable for years and years and years in fixed patterns. And the patterns are pretty solid. As I said, on the one in the south, we actually saw another cyclone drift up there and try to push its way in and get rejected. So we're working on how to explain that and why that's happening. And there's some stuff going on. People have it a little bit figured out. I guess I forgot to put in a picture of it, but if you just say, I've got a rotating planet and it's rotating really fast like Jupiter, and I have a storm, what will it do? And it turns out if you put it all together and take into account the Coriolis force and everything, storms that are rotating one direction, cyclones, will drift north or away from the equator. So if they're in the south, they'll drift south. And anticyclones, storms turning the other way, will drift towards the equator. So having the storms pile up at the North and South poles isn't too bad, isn't too surprising. You have to explain why they last so long. You have to explain why they don't eat each other and turn into one giant storm or cancel each other out. And you have to explain why the pattern is stable and why do I have 8 in the north and 5 in the south. We're partway through that. The basic idea is if you look carefully at these storms and measure the winds and everything by successive pictures, you can see that while the center of the storm is rotating one way, there's sort of a band on the outside that's kind of rotating the opposite direction. And those tend to make them push each other apart when you do the math. And then if you work out the size of these things and the size of the central cyclone, they're about the right size. So that's what fits around here. They're a little smaller in the north and you can fit 8. They're a little bigger in the south and you can fit 5, but you can almost fit 6. So it kind of makes sense that a 6th one once in a while almost fits in there and then gets pushed out. Doesn't explain why they're the sizes they are and why they're different in the north and the south, or how you get that counter-rotating anticyclonic vorticity on the outside of the storms. We're still working on that, so the basic answer is we don't know. Okay. Remember I mentioned the dilute fuzzy core down in the middle. So that leaves us with all kinds of crazy questions. The way we know it's there is when the spacecraft falls past the planet, gravity is what's making it fall. That's what determines its speed. And we can measure the speed of the spacecraft with ridiculously impressive precision, because when an object is coming towards you, the light or the radio waves it emit gets shifted a little bit to higher frequency. And when it's going away from you, they get shifted a little bit to lower frequency. That's called the Doppler effect. And it's tiny, it's small. Basically, it's the ratio for radio waves, because they travel at the speed of light. It's the ratio of your speed towards or away divided by the speed of light. That's how much you shift it. Spacecraft is moving even at 20 or 30 kilometers per second. That's still a small fraction of the 300,000 kilometers per second of the speed of light. But you can measure the precision of radio waves incredibly well. Radio waves, in this case, at about 30 gigahertz, so 30 billion cycles per second, we can measure the frequency to a tiny fraction of 1 cycle, 1 hertz. So we can measure it really, really well. When you do that, you can measure the speed of the spacecraft at levels that are you can think of them in microns per second. So as it falls back past the planet, even pretty small effects from gravity give us a measurable effect on the spacecraft. And the planet is rotating every 10 hours, twice as fast as the Earth and more than 300 times the mass. So it bulges out in the center. It's a fluid. So as the spacecraft falls past the equator, it's going to speed up and slow down as it approaches and then recedes from that bulge. And if the core in the center is compact and dense, it's going to bulge a different way than if it's bigger and fuzzy or not as dense. So by measuring how the spacecraft speeds up and slows down, we can fairly accurately measure what's going on with that core down in the center of the planet, even though we can't see it. That's how we know it's a fuzzy core, that its radius is so big. It's diluted, it doesn't have sharp edges. And that leads us right away to, how do we get that? Where did that come from? People are still working on lots of different theories to try to explain that. One of them that seems to work, but is somehow not very satisfying, is what planetary formation folks often go to when things look bizarre. And they say, well, something big hit it. Imagine an impact of an object a substantial fraction of Jupiter's mass, fairly late in the formation of Jupiter. That would stir everything up, and it might not have all settled down by now. That's one of the theories being worked. It's not the only one, but it makes for a pretty picture, so that's why that picture is here. The real answer to what's going on and why is stay tuned. And we also want to look and see if there's an even denser core down in the center. There could still be the heaviest materials all the way in the center of Jupiter, making something more compact than what we see now. Okay, so that leads us to another gravity measurement and how it impacts the magnetic field. Remember, I said we expected the magnetic field to be kind of smooth and simple, right? Because even though we're seeing it from close up, we're not seeing it from so close up that we should see all the bumps and wiggles that could be there from the liquid metallic hydrogen. Well, what we see for a magnetic field is drawn here in this model based on all the measurements. Waiting for it to, oh, it's not, there it goes. Okay, so as it spins around, you can see the south does look kind of like a dipole and not too different from the Earth. But the top is crazy. We see not one pole of the magnetic field like in the Earth's North Pole, but instead we see all these different places where the magnetic field's coming out of the planet, very asymmetric. The south is completely different from the north, and a really strong magnetic field spot, what we're calling the great blue spot in the equator, that's just popping out of the middle of the planet. So Jupiter's magnetic field looks frankly bizarre, and we're trying to understand why. So the leading explanation for that is that even though the bulk of the field is generated in the liquid metallic hydrogen layer, there's a much shallower region where the pressure is high enough that hydrogen gas is partially conducting. So it's not broken up into atoms, it's molecules. And those molecules are occasionally hit hard enough that it strips off an electron and they're partially ionized. Conduct electricity about as well as salt water. But if it's all moving around, that's enough to perturb the magnetic field. Still doesn't explain why the south is so different from the north, but at least it gives you a possibility for why the magnetic field looks distorted. And if you look at the picture over on the right, that great blue spot, remember the spot where the magnetic field sort of sticking out sideways, has distortions in it. And our latest measurements, also our measurements combined with observations from 30 years ago that were done by Voyager, that were, or Pioneer, I forget, one of the earlier spacecraft, that were not as precise by any means, but still saw something. You put those together, and what we see is it's being distorted by the winds. That black line shown on here is the surface winds on Jupiter. Now remember, I said the belts and zones go 3,000 kilometers deep. So where do you think is the depth that hydrogen gas starts to be ionized enough to conduct electricity a little bit? 3,000 kilometers deep. So we think what's going on is those belts and zones, the zonal winds moving in opposite directions, as shown in this little movie on the left, the lower left, are actually sweeping the material around and causing perturbations in the magnetic field that stir it all up and make it look crazy in the north like that, and distort the great blue spot. And we actually see it changing a little bit with time, and we see it distorted in a way that matches the winds. So we think the deep winds are blowing the magnetic field around. And we think the reason that they go only a few thousand kilometers deep, which is still pretty deep, but we think what stops them is probably they're getting deep enough that the magnetic field is slowing them down. Okay, so that's all kinds of stuff about what we learned. There's tons more. I hope I provoked a bunch of questions, but let me tell you a little bit about the extended mission as well, because we just finished our prime mission. We got the 32 science orbits that we promised, and everything is still working, and NASA has just given us permission, and more importantly, money to keep going. So I want to talk just a little about what we're going to do next. And the heart of that comes from the fact that our orbit is changing. Because Jupiter is not a perfect sphere, and we're in this big elliptical orbit, the line of absides of the orbit, that's the direction that the long part points, shifts every time we orbit Jupiter. So if you look at the gray line here, our very first orbit around Jupiter, Perijove, the part closest to the planet, was just 4 degrees north of the equator. But each orbit, it moves north by almost a degree, so that by the time we get to where we are about now, we're actually a little past Perijove 34. We just had Perijove 37. But Perijove 34 was this blue line where our orbit is tilted so that our closest approach to Jupiter is 28 degrees north of the equator. And if you wait long enough and the spacecraft survives long enough, by the time we get to Perijove 75, which is about where we'll run out of fuel if the radiation doesn't kill us, our Perijove will be at 63 degrees north. So our first orbits do a great job of looking at the planet down here near the equator. But by the time we're in Perijove 75, we should be able to do a great job of looking at Jupiter way up here near the North Pole. And remember, our very first discovery was the poles don't look anything like the equator. So we're expecting to find all kinds of surprises and to learn more about the deep atmosphere and the gravity and things like that with the extended mission. In addition, if you look at what those orbits do, so here's the first orbit coming in. I'm not showing the whole orbit because then you wouldn't be able to see anything. Jupiter would be too small. But coming in, it goes around the planet, ducks inside the radiation belts, and comes out the other side. By the time we did orbit 34, we were crossing the equator. Instead of way out there to the left, we were crossing it at the right distance to go by Ganymede. So we did a flyby of Ganymede, and we used it to change our orbit period a little bit to be a little faster. And then if you wait till perigeo 45, which is late next year, we'll be crossing the equator at the right time to fly by Europa. So we're timing that to get a close-up of Europa and use all our instruments that are designed to look at Jupiter to look at Europa in a way that hasn't been done before. Then if we make it long enough, if we survive and the radiation doesn't kill us, we get a couple of orbits that go right by Io. And if we really survive a long time and the radiation is a lot less dangerous than we think it is, we'll get to fly by through the main ring, the fairly faint compared to Saturn, but still pretty significant rings that orbit Jupiter, and maybe learn something about the rings close up. So that's the extended mission. That's the surprises from Jupiter. And what I'd like to do is take however much time you guys want and answer questions about Juno and Jupiter, or pretty much anything else. I can answer any question because I'm good at saying I don't know or I don't want to tell you. Oh, and I almost forgot, I should say, take a look at these websites, especially if you do astrophotography or any kind of image processing. Take a look at the Mission Juno website, because what we do with our visible light camera is we don't have a science team for the visible light camera. It's an outreach camera. What we do is we post the images, the raw data pretty much, on a website, and we let the general public play with it and make pictures. So there are people who are really good at stitching them together and taking all the little tiny images and making mosaics and putting the 3 different colors together and making a color image. And there are people who use the results of that from other amateurs and play with the color scale and the stretch, or put them together and make movies to make really interesting things. All these images you're seeing here are, right now, these are the raw stuff that we just dump out there. And then if I go over here and what I'll do is I'll pick the featured ones. So those are the ones that one of our scientists, Candy Hansen, has picked and said, hey, these are really cool. So these are all pictures made by just volunteers. Anybody who goes on the website, signs up and submits it. And some of these are really cool pictures. These are the new ones. Gerald Eichstadt, he's one of our stars. He's an amateur. I don't think he even does amateur astronomy, but he does image processing, and he loves to put these things together and make great pictures out of them. Anyhow, lots and lots of these things. I won't try and go through it because it'll take hours, but I encourage you, if you like to play with images in any way, go take a look at the Mission Juno site and volunteer and have fun. All right, I want to stop sharing my screen so that I can see your faces and see if we have any questions. So let me get out of that, out of slideshow mode. Stop sharing. There we go.
There you go.
Okay. I think we're a small enough group. People don't need to raise hands or put anything in the chat or anything. Just speak up if you have questions or comments.
And I muted some folks, so you make sure you unmute yourself, okay?
Steve, I just have what's probably an easy question. It's a solar powered mission,
Right.
but you mentioned running out of fuel, so I was a little confused by that.
Okay. So the solar panels provide around 500 or 600 watts, which is enough to light, say, 6 old-fashioned light bulbs, or not enough to power a small refrigerator or air conditioner. But it's enough to run all our instruments and the whole spacecraft and the computer. So we run it on electricity from the solar panels. But that doesn't help us move. And in every orbit, we need to adjust the orbit a little bit. If we want to pick a particular longitude, we speed up or slow down just a smidgen. And out of the 53 days or now 43 days that we're orbiting around Jupiter, if you slow down just a smidgen, and with Jupiter rotating every 10 hours, you can pick whatever longitude you want, because by the time you come around again, you can be an hour or 2 hours or 3 hours off from where you were going to be and get the longitude. But that takes a little bit of fuel. And we also have to maintain the altitude. If we get too close, we don't want to hit the atmosphere and burn up. And we don't want to be too far from Jupiter, because then we'll be in the rings of dust that could hit the spacecraft, or the radiation that could fry us. So that takes a little bit of fuel as well. So every orbit, we have to fire the thrusters a few times. We needed a bunch of fuel and the main engine to get into orbit around Jupiter. But once we put it in the 53-day orbit, we don't need the main engine anymore. And the way we control the rest of it is just bleed a little gas out through thrusters. So the fuel is just being used the way you let the air out of a balloon to push the spacecraft around a little bit. Our estimate is, if we're careful that and do just the maneuvers that we think are really important, that we will have enough of that gas that will run out somewhere around orbit 75. However, our estimate of the radiation, remember, we're getting closer and closer to the planet every orbit now. As our orbit comes in, the place where it crosses the equator is closer and closer to Jupiter. That means we're getting more and more into the radiation belts. The radiation's getting worse and worse every time. And we don't know, but I don't think it's going to survive all the way to orbit 75, because I think the radiation is going to eventually destroy something important before we get there. So we'll see.
Thanks.
Right. You'll find I give long answers to simple questions.
Right. That's great.
Steve, I have a question.
They need a plan, Jen, or?
Earlier in your presentation, you talked about the atmosphere containing ammonia and water, and there was lightning. And those are the conditions that were similar to the Urey experiment from the 50s.
Yeah.
Have you guys found amino acids dropping out, or can you detect them?
No and no. We haven't found it, but we're not able to detect that. However, if you look at Jupiter and say, is this a good place to find life similar to life on Earth? Pretty much everybody who does that says, nah, this is not a great candidate. And the reason is that, remember, if you go relatively shallow depth into the atmosphere, you're getting to temperatures that are so high that everything's vaporized. And if you go relatively shallow distance from the optimum temperature out of the atmosphere, so up in the atmosphere, you're getting to temperatures so cold there's not enough energy for any kind of life similar to ours. The sunlight is really weak, so you're not going to have stuff that gets its energy from the sun. It's going to have to get the energy from something in the atmosphere. And there's all these storms carrying stuff up and down. So the guess is, to have life there, you'd have to have something that could float in the atmosphere at just the right height to be the proper temperature, handle these giant storms, and somehow control its altitude so that it didn't get too deep and vaporize or too shallow and freeze. However, it turns out Europa, one of the moons of Jupiter, is a way better candidate to look for life like ours. if you look at Jupiter's moon Europa, which we're going to go close to in about a year, a little over a year, surface of Europa is covered with ice, but we've known for a while from the cracks in the ice that underneath that ice is an ocean of liquid water. So how do you get liquid water underneath the ice in a moon that's way out far from the sun? Well, it's got to be tidal heating from Jupiter. It's got to be the fact that Jupiter's gravity is, slightly weaker on the part of the moon that's close to Jupiter than it is on the part of the moon that's far from Jupiter. So that can have a heating effect. It has enormous effect on Io. It's so hot that you get volcanoes and stuff. But that's probably what's keeping the water liquid down inside Europa. And why is that exciting? Because that means that the heat is coming from the bottom of that ocean. So the warmest part is going to be at the bottom. It's going to be something like volcanic vents on the Earth at the bottom of Earth's ocean. And you mentioned the experiment with ammonia and lightning. The other experiment that's really exciting and holds a lot of promise to explain how life formed here on the Earth simulates conditions of deep ocean vents. So people are really excited about the possibility that some kind of life, somehow similar to life on the Earth, might have formed in the ocean underneath the ice on Europa. Juno was not designed to study Europa. Our main task regarding Europa was to stay the heck away from it so we don't contaminate it. But we are going to get a couple of flybys in a year or so, and we're going to do what we can. Probably we don't have the right instruments to look for life, but we can look to see maybe something about how thin the ice is. If you're going to go look for life on Europa, you'd like to know, is that ice 10 meters deep or 1,000 kilometers deep? It's going to change your answer quite a bit about how you look. And maybe we can look for plumes, see if water is actually, if there's cracks in the ice that come all the way out, then water could be spewing out into space. And so the next mission could maybe look for life in those plumes. There is a next mission. There's a project called Europa Clipper that's planning to send a spacecraft to study Europa. It's not going to get that close to Jupiter. It's going to orbit Jupiter in an orbit that lets it fly by Europa a very large number of times. But we're hoping to feed them a little bit of information from our observations before it's too late for them to change anything about how they run their mission. It'll be too late to change anything about what they're building because they're already most of the way through all the designs and started building stuff. But at least by the time we get some Europa data, maybe we can say, hey, look at it this way, or the radiation is stronger than you thought or weaker than you thought, and you can do different things. So we're going to help a little with life, but nothing directly. Juno was not designed to look for life, and we don't have any of the right tools unless, somebody's sending us a radio signal, right? That's
Steve,
what
I have a question.
Yeah.
Well, first of all, a comment. Have you ever read, or if you haven't, I suggest you read Arthur C. Clarke's story, A Meeting with Medusa. Have you ever read that one?
Been a long time, but yes.
Yeah, that's an amazing story about life in Jupiter. But anyway, I want to make sure you're aware of that. It's a wonderful story. But my question is the cyclones in the northern and southern polar regions. Is that behavior related at all to I think, a hexagon we see on Saturn's poles?
So the answer is a definite maybe. If you take our latest paper that's just out that talks about a sort of speculative simple model for the cyclones, in that paper led by I think it's Eli Galante, anyhow, the group in Israel that works with Yohai Caspi. They put together a sort of toy model of how it all works, and they went ahead and applied it to Jupiter or to Saturn and said, does it work on Saturn? And their answer was, given the size of the storms on Saturn and the conditions and how fast Saturn rotates and all of that stuff, that, yeah, their model kind of works on Saturn and predicts that Saturn should not have these clusters of cyclones and should have just one at the poles. So that hexagon we see is really sort of a storm-like structure at the pole, surrounded by jet streams, and that make it look like a hexagon. And that kind of fits with the model. But it's really only a toy model. And in my opinion, the biggest thing it's missing is any reason for why the storms are the sizes they are. It's one thing to say, okay, if the storms are these size, then you're going to get these patterns. But that's kind of like saying, if I pack some marbles together, the size of the marbles tells me how well I can pack them around. It still doesn't answer the question, why are they that big and not bigger or smaller? So it's kind of a maybe. Since we talked about life a little bit, I should say one of my other hats is I've worked on the search for extraterrestrial intelligence, looking for radio signals a number of ways. And I always like to remind people when we talk about that if you think about how life on Earth formed and take that as our best guess as an example, it took 4 billion years from when life formed to when we had intelligent life, or for that matter, anything as complicated as a mouse. So if I were to pick randomly a star out in our galaxy and assume that every star has planets, and every one of those planets, every system, there's at least one habitable planet, and that life forms pretty much the same way it did here on the Earth, those all started at different times. So if I only assume that radio waves, that civilization generates radio waves for 1,000 years, right? We've had them for less than 100. But suppose we generate radio waves for 1,000 years, then I've got about a 1 in a million chance for any given star that somebody is sending radio waves out right now, because it could have been any time in the last several billion years that they formed. So their civilization could be way beyond ours, or there's nothing on the planet as complicated as a cockroach, right? So the SETI searches that I've worked on have always focused on look at a really, really large number of stars. There's 100 billion stars in our galaxy. So 1 in a million, that's going to happen 100,000 times. But it won't be the stars that are close unless we get really lucky. Anyway, that's an aside. I know nobody asked me about it. I just thought I'd get on my soapbox for a minute.
I have a question about, since you've studied the atmosphere, do you have any more insight into why the big red spot and what causes it to dim and then brighten again?
Yeah. So we're actually learning quite a bit about it. There's another paper by Chung Lee from University of Michigan, but it's not out yet. So I don't want to steal his thunder before it gets published. I'll just say the microwave radiometer lets us see not just the depth of the great red spot, but a combination of the temperature and what it's made out of. So it's not clear cut. It's not like, oh, this is the temperature at that spot, and this is how much ammonia there is. But if I dial up the ammonia, I have to change the temperature to match in order to still fit our data. So you can put that together and try and figure out a little bit more about the great red spot. We already knew that the color, the red, is chemistry. We don't know the exact chemistry, but we know that it has to do with, almost certainly, with how long that material has been there in the sunlight. So the red is probably just the top of the clouds, and the white is new material. So part of when it changes is just material getting stirred up or down, and isn't really a big change in the storm itself. You do see big changes in the storm, though. If you look over the last 20 or 30 years that we've had good pictures, or look over the last, whatever it is, 100 years that people have been looking at it and at least making drawing, the great red spot has gradually shifted from something that's maybe 3 or 4 or 5 times as long as the Earth is wide and the same height more or less as the Earth to something that is now almost the size and shape of the Earth, at least in cross section. But we don't know exactly what's going on. It's obviously the energy comes from the heat leaking out from inside the planet. And as I say, watch over the next few months or a year for, press descriptions of what's in this newest paper. We have some ideas. Oh, and I should show you, let me find it and share my screen again.
Magnetics.
Let's see, I think
Uh,
it's going to take just a minute to find this, but I think it's worth doing.
But now it's getting more compact.
Let's see, so that's not the one. We have a little
Somebody said it's
image that kind of shows the
no.
size and shape of the great red spot, and it's not what you'd expect. So I want to try and find it and bring it up. This one, yeah. Okay, so let me share my screen again, and then I'll make this picture bigger in a second. Okay, so obviously this is a fake picture, right? But the point of it is to give you the scale. We put in the Earth for scale. And to give you an idea of the depth, this is about the depth of the Great Red Spot. So it's very deep. It's hundreds of kilometers deep, but it's enormously wide. So its shape is kind of like a pancake.
Mm-hmm.
And I wanted to show that because when we think about the storm, it was surprising how deep it is, but it's still basically a flat object. And so whatever it is that's making it last a really long time is probably not some kind of connection deep down inside the planet. It's got to be something to do with how storms this big work. And the other thing I wanted to show from this scale, we don't have a hurricane shown on this picture of the Earth, but a hurricane, a really big storm on the Earth would be, sort of that big, right? Half the size of the US or something. And a storm like that might last for weeks. Smaller storms don't last as long. A small storm might last for days. Well, this is a storm bigger than the whole Earth. So part of why it has lasted for many years has got to be just related to the size. Bigger storms last longer. All right. Let me go back to where I can see you.
I have a question. There was recently an amateur astronomer that had discovered that Jupiter had received an impact from an asteroid of some sort. And I was just wondering if you had able to use Juno to look at that at all. And if an impact stirring up the atmosphere would give you some information.
An impact stirring up the atmosphere would give us some information. We didn't see it, which tells us that it was small enough that it didn't cause enough disruption for us to see with our cameras. And we had a view of it within, I think, if I remember right, just a few days of when it was seen, when the impact was seen by the amateur, which says that you probably should be thinking of it as a large bolide rather than a small asteroid. So that's kind of the most we were able to say about that particular one. In general, people are paying more attention to Jupiter the last few years because our spacecraft is there, and we have a program to coordinate with the amateurs who do such a great job of studying Jupiter and getting really good images. And they've seen a lot more impacts. And we think that's not that Jupiter's getting more impacts lately. It's just that we're now able to see it with a lot more telescopes looking at it with a lot better quality data. But nonetheless, it means Jupiter gets hit fairly often. This was a particularly big, bright one, but maybe isn't quite that rare. So that's about all I can say about that particular one. We saw bolide with the ultraviolet camera on Juno. We got lucky once and saw something in the ultraviolet that we're pretty sure was a big meteor. The other thing I should say, I guess, I don't know how many of you do astrophotography, but some of the people contributing to the science are amateurs with, big telescopes for an amateur. We're talking about things that are a couple feet across aperture. But what really makes them valuable is the lucky imaging technique. You guys know about this, stacking the images?
Mhm.
That has come such a long way in the last decade or two that now you can get amazing quality images from the Earth of Jupiter. You still don't get the vantage point of a spacecraft, but you can do that every night, and there's enough people out there doing it that we rely on getting images from the amateurs for context for a lot of the science that we can do.
Steve, I know a lot of the things you talked about, you said, we have a leading theory or we're not really sure and so forth, but I'm wondering, based on all the data you have so far from the Juno mission, has it significantly changed how we think Jupiter formed and whether in fact it did form closer to the sun and then over time moved out? In other words, has it changed any theories about formation and even timing of formation from what we had previously?
Yes, but mostly what it's done is tell all the theorists, you got to go try again. None of these are working. It's not quite that bad. A lot of the
job security, right? That's
right.
What you said.
The theorists mostly, for many of the theories, say, "Oh, I don't have to tweak this very much to make it work." But here's what we see. We don't have a truly global water measurement because the planet is so different with different latitudes that we don't trust that the measurement we have extends over the whole planet. But at the equator, we measure what we're pretty sure is the deep water content to be about somewhere around 3 or 4 times solar. So what that means is you take the ratio of oxygen to hydrogen, and then you compare that ratio to the same ratio, oxygen to hydrogen, in the sun, and it's about 3 times or 4 times larger on Jupiter than it is in the sun. That's a really interesting number because for some of the other elements, we do have a decent measurement, and many of the heavier elements on Jupiter show up at about 3 or 4 times solar in the upper atmosphere. So if you think about how that formed, if Jupiter formed from ice that was cold enough to be ice, but not super, super cold, so say roughly where it is now, that far from the sun, then the other heavy elements that are gases could have stuck to those icy planetesimals or whatever, but it probably wouldn't have all stuck the same way. The more volatile stuff would escape more, and you'd carry in more of the things that didn't escape. So the ratios of the different elements would be not all the way up to what the ice is, the water, right? So the water, there should be more water than, say, nitrogen by comparison, comparing to the sun. And the different elements should come in different amounts. But that's not what we see. If, on the other hand, the icy pieces that made up Jupiter formed really far from the sun where it's super cold, then basically anything that hits the ice sticks. So now all of the ratios of all that stuff should be about the same. And so the ratio of nitrogen to hydrogen on Jupiter should be similar to the ratio of oxygen to hydrogen when we compare it to what's in the sun. So you get however much nitrogen you had, if it hit the ice, it stuck. And so you get that same ratio, and then the hydrogen and helium didn't stick, but gravity eventually sucked them all in, and you got a whole lot more. So that says that what we've seen so far with that one measurement at the equator is consistent, more consistent with things formed cold than things formed close. But there's other problems and there's ways around it. If you form from little tiny pebbles instead of great big chunks of ice, then you have more surface area and maybe you can carry more stuff in and make it fit better. And you're still left with the problem of the deep core. So if the core of Jupiter if you don't have the right amount of heavy elements falling down in the core to match up with what should have come in, then the theory isn't working very well. And the gravity folks, when they look at the core and everything and try to explain it, have problems explaining what they see if the amount of water is what we're seeing at the equator. So the people analyzing the gravity are saying, I think the water should be less than solar. And the people analyzing the radio data at the equator are saying, well, here in one spot at the equator, it's 3 or 4 times solar. Somehow you have to make all of that fit, and we're still putting the pieces together. I don't think you can take, there are some theories you can throw away, but I don't think you can narrow it down to 1 or 2 basic models and say, yeah, this one is right.
Thank you. Thanks.
Sure.
I have a question regarding the flyby of Io. When you go there, will you be going through the area where the volcanic plumes come up off the moon?
I don't think we'll be close enough to actually fly through a volcanic eruption. We are going to be really close. If I remember right, it's a few hundred kilometers. But I don't think that's quite close enough to to get hit by stuff ejected from a volcano. We're flying essentially as close as we can, or at least as close as we can manage to do it twice, because we want to use the gravity to try to figure out about the molten inside of Io. There's some debate as to whether the whole inside is molten or some part of it and how deep that goes and things like that. And we might be able to figure that out from the gravity.
Thanks.
When Alan Stern was asked about how New Horizons changed our view of Pluto, he gave a very impassioned answer about how we went from thinking of Pluto as nothing but a sort of a ball of ice and very uninteresting to being something fascinating. And it seems to me that the Juno mission is perhaps, and correct me if I'm wrong, made us think of Jupiter as something much more than just a failed star and into something much more interesting. What would you, as an investigator who's looked at this very closely, what would you like to see the future missions to Jupiter do?
Yeah. Well, I think Europa is really interesting. I'm excited about the Europa Clipper mission and looking for life in Europa, but that's kind of dodging your question because that's not really Jupiter, that's orbiting Jupiter. I would like to figure out a way to see even deeper than the microwave radiometer can see into Jupiter's atmosphere. When people first sent, the Galileo spacecraft dropped a probe into Jupiter in like mid-90s. The people who built that probe were pretty confident that it would survive below pressure of 20 bars, 20 times the Earth's atmosphere. And they picked that number because that's what everybody thought was deep enough to learn about the whole planet. We now know that was totally wrong. When we designed Juno, we were really confident we would be able to see down to at least about 100 bars. And we were very confident that should be deep enough to teach us about the whole planet in terms of the atmosphere. We were totally wrong. So what I would like us to come up with, and I don't have an idea for how, is something analogous to the microwave radiometer that can see through the clouds but can see to 1,000 bars. And maybe don't be quite so confident that that's deep enough, but at least 10 times deeper. Now, our lowest frequency channel that sees the deepest, it's picking up a little bit of information from really deep, maybe as deep as 1,000 bars. So it's possible that we'll get that by somebody smarter than me figuring out how to do data analysis that can pick out just the part that came from really deep. I kind of doubt it. The bulk of what we're seeing with that instrument is at 100 or 200 bars. But that's one possibility, is coming up with a better way to use the same radio technology, but sort of filter out the shallow stuff so that you can see the really deep stuff. As I said, if I had an idea for how to do that, I'd have proposed it to NASA by now. But that's what I really would like to see, is a way to look 10 times as deep into the atmosphere and see if we can finally reach a depth where we understand what's going on. Everything's, fairly well mixed. If there is such a depth, it may be that no matter how deep you go, you see structure, and that would be really, exciting to learn as well.
Thank you.
Great question. Oh, and I should say too, if you put together what Alan Stern said and what I said at the beginning of this talk, there's a bigger lesson, right? The bigger lesson is you have to measure because you don't understand it until you do. And every time we think we understand something that we haven't measured, we're probably wrong.
Have you ever seen the movie Europa Report, Steve?
No, I haven't.
Oh, you should check that one out. It's wonderful science fiction.
Uh-huh.
And I'm not going to tell you any more on that, but try to see Europa Report. It's very, very, very nicely done science fiction movie. I wouldn't call it a great movie, but it's a really good movie. So I think you'd enjoy it. It was fun. Yeah, definitely. It's a good night for science fiction discussion too,
Yeah. I mostly find, I like science fiction movies, and I like science fiction books and stories even better.
Mm-hmm.
I like to play the game of, figure out what's wrong with the science, because it's almost impossible to write fiction that doesn't make some kind of science or technology mistake somewhere. But I also think that even though everybody gets the science wrong somewhere, that's not the purpose, and the ideas are always really interesting and often lead to, we should see if we can go try doing that experiment, or you can get ideas for how to do science out of the science fiction as well as just
Europa Report carried a lot of respect for science, so I think you might enjoy it.
Cool. Did I hear one of the people on the line today is a science fiction author?
Jack McDevitt there, Crypt. Yeah. He's a Nebula award winning.
So Jack, I don't know if you probably have more ideas than you know what to do with, because coming up with the ideas for science fiction stories is probably not the hard part. But there's something that for the last couple of years has really sparked my imagination, and I don't have the talent to write a story about it. So I'll tell you anyway, and you can throw it out, with all the other ideas that people give you for no reason. But there's an experiment that was done, a quantum mechanics experiment a few years back, where they looked at, it's called a Mach-Zehnder interferometer. But the important point is that if you send a photon through this system and don't measure its polarization, you get a diffraction pattern. If you do measure its polarization, it comes out definitively in one of two detectors. That's a well-known quantum mechanics phenomenon. But what they did is they entangled two photons so that one of them should have the opposite polarization of the other. They sent the photon several hundred kilometers in the Canary Islands to another island and randomly either detected it or not. And then after the fact, they went back and said, what are all the ones we detected? Let's make the pattern that they showed up in the detector. And what are all the ones where we didn't measure the polarization? Let's look at the pattern that they showed up in the detector. And they got the two differences. They got diffraction for one and straight up detection for the other. And why that's pretty amazing to me is the ones that they were looking at the pattern in hit their detector before that other photon ever got to the other island to be detected, right? Several hundred kilometers versus a few centimeters.
Wow.
Interesting. I have a story now that is waiting to be looked at by Nature magazine. Title is, that's not exactly what you're talking about, Steve, but get a sense from the title. The title is Quantum Blonde. I'll let it go with that.
I'll be watching for it. Anyway, I think there's something fundamental we don't understand about the universe, and quantum mechanics is exposing it. And I wouldn't be at all surprised if our concept of causality, causes come before effects, simply has to be abandoned.
Cool.
Sorry, I know that's way off topic.
That's quite all right. Quite all right.
It's also really hard to follow up. It's like,
Well, it wasn't my intention to shut down the conversation.
oh no, it's just an interesting idea.
Anyone have any other questions for Steve?
I have one, if I may. Steve, if there were a major discovery to be made over the next few years, and you could make the call on it, what would it be? What would you like to be involved with that goes deep into this issue?
Wow. Well, I'm actively involved in looking for life in outer space and looking for signals of extraterrestrial origin, intelligent signals. I'm not especially optimistic that that'll happen in my lifetime, but I think that would be possibly the most important discovery in the history of science. In fact, I put that in a proposal that actually got funded. I was, asking for money to do this radio search, and I basically said, you judge these things based on the likelihood of making a discovery and how important this discovery would be. And it's presumably very unlikely that we'll make this discovery, but if we do, it'll be the most important discovery in history. And they funded the proposal, so somebody thought that was, if not true, at least close.
Why do we have so much passion in trying to find life out there? Why does it matter so much?
To me, especially intelligent life, it matters because it's the difference between we are unique and special and we are part of a community. Those are both, things that you could aspire to, but they're very different. If we treat our world and each other as if we're the only ones around, that's very different than if we recognize ourselves as, one of many and part of a community that supports each other or potentially could support each other.
I think they'd want us.
Boy, this is a night for philosophy.
Welcome to the Chester County Astronomical Society.
We do astronomy and philosophy.
They go together well.
Yeah.
When I'm done with the Asimov that has Jack's story about Tau Ceti, I will send it to you. You need to read that.
That's probably, let me take a quick look. Is it on Apple's iBooks?
As I'm off, I'm not sure, but it's a November, December issue. And Tau said he said what?
Or-
It's a very short story. It's very a lot of fun though, really fun. So. Well, that was a great
Like,
talk.
It's not
Thank
that
you.
easy. I'll have to write it down. Because I don't, not only should I, do I not want to wait till you're done and mail it to me? But, also because the author should get
Royalty.
the royalty.
You can get it on Kindle.
I'll take a
We're
look. and
talking
I'll
about a
find it.
magazine here. It's,
That was a wonderful presentation. Thank you.
Yes, thanks
Thank
so much,
you.
Steve. Really
This was
appreciate
fun.
you taking the time. Thank you.
It's only 6 o'clock here, but I realize it's 9 o'clock there.
Thank
Yeah.
you very much.
Thanks.
Yeah, thank
Steve,
you.
I'll be in touch with you, Steve. Thank you.
That's great. Good
Thank
night,
you.
everybody.
thanks to all.
Thank you. It was very enjoyable.
Thank you.
Hey, Dave, I need to talk to you at some time. If I can.
Absolutely.
Okay, give you a call over the weekend. Is that all right?
Absolutely.
Okay,
Let's talk.
great. Thanks. Thanks, everyone. Have a good night.
That was a great one.
Right.
Thanks for
Right,
arranging,
thank
Bruce. That
you.
was fun. Jack, thanks for tuning in.
Thank you. Well, my pleasure. Thanks
All
for
right.
the rescue.
That was a
All
fantastic.
right, guys.
Bye-bye.
Nice to see everybody.
Yep.
See you later.
See you in December live, I hope.
Okay, yeah, absolutely.
Be here.
Yes.
Ah.
Sure.